start. I hope
Good
the
morning, ma'am.
same today itself. Good morning, good morning, good morning. A very good morning to all of you, and I'm glad that you really made my day. Before time, you were present. I'm very happy about it. So we will start with a happy note. Okay?
Ma'am, can I start reading
Yeah, sure, sure.
from that red one?
When an object vibrates,
Okay. When an object vibrates and makes sound, the air layers and around
around
it
it.
also start vibrating in exactly the same way and carry sound waves from the source to our
Our
ears.
ears. Don't break it up. Okay? Don't stop in between. Don't
No,
pause
ma'am,
in
I'm
between
not
the
stopping,
words.
but my screen is small, so I have to zoom. That's why I have to
Okay,
that scroll
okay,
down.
okay, okay, I can understand. Okay, then I'm sorry, I take my words back, better. I'm sorry, I did not know. So I can understand. Fine. Because, the meaning, uh, it loses the meaning. When you pause in between the words, the impact is less. Okay? That's the reason I had said. Doesn't matter. At least you are
I
trying, I'm glad. So, what is it?
okay.
When an object vibrates, for example, this is the pendulum. It starts vibrating, it goes here, then it goes here, right? So the pendulum is not moving. The particles around the pendulum is moving. Hope you understand. See. And then it reaches us. What do you say? Then it reaches us. And then we hear. Because of the vibration, the energy is moving from one particle to other particle till it reaches our ear. And when it reaches our ear, we can hear the sound. Is it clear?
Yes.
Is it clear? So what is going, beta? The energy is going. The particle is not moving. The particle is only vibrating. It is not moving from its place, it is vibrating. Do you understand? The particle from here is not moving to my ears, but it is vibrating and the energy is moving to our ears. Is it clear to all of you? Is it clear to all of you?
Yes, ma'am.
Okay. Second point.
Air layers, air molecules vibrate back and forth about their mean position.
Same way like pendulum. The air particle is moving here, then it's moving back. So it is moving back and forth. And this is the mean position. What is the mean position? This is the mean position. Is it clear? So going to and fro is like back and forth. It's like swing. Okay? It's like seesaw. So that movement is called as oscillatory or back and forth motion, right? So that's how it is moving. Next.
When the layers approach each other, they form
Form.
compression, and when they move away from each other, they form
Rarefactions.
rarefaction.
Say rarefactions. This is how it is
Rarefactions.
exactly. This is how it is pronounced. I think I told you this one. See, what is this beta? Compression. What is this? Compression. Is it clear?
Compression.
All of you understood? Okay? So this is compression. Okay. Now what is in the center? The particles are away from each other. The particles are like this. You got it? Away from each other. This is rarefaction. Hope you understood? So in between two compressions, what do we have, beta? It is rarefactions. So it is alternate. Compression, rarefaction. Compression, rarefaction. Is it clear? Is it clear to all of you?
Yes.
Okay. Now next.
Note that there is no actual movement of air layers from the source of sound to our ears, but the sound energy is getting transmitted from one layer to another is succession.
In
Succession.
succession. In
Succession.
succession. Succession.
Succession.
Thank you. Now air layers are not moving. But what is moving? The energy is moving. The energy is getting transmitted from one layer to another repeatedly. What is the meaning of succession, beta? It is repeated. You understand? So the energy that what is repeated compression and then rarefaction. Again compression then rarefaction. So can we see that in succession? The layers in succession, can we see that? Boys, are you getting me or not?
Yes,
Hello,
ma'am.
boys. Do, are you understanding what I'm trying to say? That what
Yes.
is written over here, the sound energy is getting transmitted from one layer to another. So what is the layer? One is compression and then comes rarefaction. Again comes compression and then comes rarefaction. So this is in succession because it is repeated one after the another. This is what has been conveyed. Is it understandable? So the layers are not moving. See, is this layer moving? No, it is at its original place. But what is moving? What is transferred? The energy. Which energy? The sound energy. Is it clear? Is it clear to all of you?
Yes.
John, are you understanding? John, are you understanding? Is he there?
Yes, he is there only.
Not getting any response from him. Doesn't matter.
Yes,
I think
ma'am.
Okay. Now next.
the maximum distance moved by a vibrating air layer on either side or its original
Off,
position is
off.
known as the amplitude of the sound waves.
Okay. Now, see, one by one we are explaining. Now, I had taught you how does the wave moves better like this, isn't it? Remember? This is how the wave moves. Agree or not? Say at least something yes or
Yes,
no. Ah, yeah. You agree? Okay. Now, what it is saying? The maximum distance moved by a vibrating air layer. So, this is the vibrating air layer. You agree? This wave is the vibrating air layer. Yes or no, beta? In the form of wave. From the original position. What is the original position? The one in the center. There is a line. This is the mean position. You agree?
yes,
Yes or
ma'am.
no, beta? Okay. Now, what they are saying, the maximum distance. Now, what is the maximum distance? Can you see this? This is the maximum distance on the either side. On the either side of the original position. Now, original position is in the center. So, either side means one on top and one at the below. Is it clear? See. Now, what is this called as? What is this called as? Amplitude. What is called its maximum distance? It is
Amplitude.
amplitude. Any problem? Any problem?
No, ma'am.
No,
Next.
ma'am.
Okay, thank you. Next.
The number of completed back and
Complete.
forth vibrations of a layer in 1 second is known as frequency of the sound wave.
Okay. Now, this is the pendulum. Now it goes here. Then it comes back. Again it goes back. Is it clear? This you agree? Which is this motion called as back and forth motion. This also you agree? Hello?
Yes,
Hello?
ma'am.
You understand? Okay. How many times does it vibrate in 1 second? That is called as the frequency. You understand?
Frequency. Okay, ma'am.
Yes.
पर मैम
The number of
फ्रीक्वेंसी तो
oscillations.
उसकी हाइट नहीं हुई वो साउंड वेव्स की जो वो होती है
Better speak in English.
मैम frequency is a type of I have a doubt that it's a type of that what uh,
It's
waves
not any
wave
type.
like
It
things
is a
wave like
notations. Just a
हाँ
moment. It is a notation, like how we talk about amplitude, how we talk about a wavelength, then will come frequency. All these are the terminologies regarding sound. You got my
Mhm.
point?
Yes, ma'am. Got
And I
it.
think I taught you. I taught you in 8th standard also.
Yes,
Just
yes, ma'am.
brief.
That's why I've
This
got a
frequency.
doubt.
Yeah, yeah. Now that's why we are coming one by one. And how this is noted? It is noted by the symbol nu. Remember?
Symbol new. Okay.
Nu is the frequency. Is it clear? We will come to it one by one.
Okay, ma'am.
Now, okay, now did you understand this much? So, how many times does it vibrate? In 1 second, that will be the frequency of that particular sound wave. Is it clear?
Okay, ma'am.
All of you? Ninth
Ah, okay.
standard? Huh? Okay. If any of you have any problem, please stop me.
No, ma'am.
Voice. Okay. Okay. Now the last one.
The distance between two succession compression or two succession rarefaction is called wavelength.
Let's go back. It becomes so easy, isn't it? Now, I said the distance between two compression. What it is? Lambda. It is the wavelength. I hope you have understood.
Yes, ma'am.
Yes?
Yes,
The
ma'am.
distance between either two compression or distance between either two rarefaction is called as wavelength. So I think you are through this slide. Any problem regarding slide? We are through. I've told you point by point all the uh, terminologies regarding sound waves. Is there any
Yes,
problem?
ma'am.
You can stop me.
Okay, ma'am.
No, is there any problem?
No, ma'am. No problem.
How does sound travel through air? Yes, it's the same thing, but in a different format. Please go through it. And if you think it's the same thing, then we can go to the next slide or you will explain. Okay, start, beta.
Am I only?
No, anyone, if no one is doing, then you continue because let's not waste time on that. Will you be able to see?
Okay, ma'am.
Yeah. Yes, start, beta.
Air is the most common medium through which sound travels. When a vibration object moves
But it
forward,
is
it
vibrating.
pushes. Yeah, sorry, ma'am. When a vibrating object moves forward, it pushes and compresses the air in front of it, formatting, forming
Forming
a region, forming a region of high pressure called
compression.
compression. The compression move away from the vibrating object. When the vibrating object move backward, it forms a region of low pressure called rarefaction. As the object moves to and
Flow.
fro rapidly, it produces a series of compression and rarefaction
Rarefaction.
in the air, which makes the sound to
Propagate.
propagate
Propagate.
in the medium.
What is the meaning of
Propagate,
propagate, beta? It is traveling. What is the meaning of
traveling,
propagate? Traveling.
traveling.
Okay, something did you understand? You read it out. Did you understand something?
Yeah, ma'am. It is same as before I had read.
Exactly. You had read. I had read. What you will say, beta?
I had read.
It's the same as before. I had read. It is the past tense of read. So how you will pronounce as read? Okay,
Okay, ma'am.
fine. So you are learning laws every day, isn't it? Fine. So what is it? What it is saying that we know that sound travels in air beautifully. It's a common medium. So which is the medium to travel? It is air. So sound travels through air. How does it travel? Any object which is vibrating, it is moving to and fro, you agree? So what it is doing? It is pushing the particles and is compressing the air which is in front of it. So what it becomes? It is becoming a high pressure region which is known as compression. Do you agree? Do you
Yes,
agree?
ma'am.
Okay. This compression is moving away from the vibrating object. I told you the energy is moving away from the vibrating object. Is it clear? So when it is coming backward, so which pressure is created? A low pressure is created, which is known as rarefaction. And if we see that the object is moving very fast, that oscillation is very fast, so then it produces series of compression as well as rarefaction, and then the sound travels very fast. Do you understand?
Yes, ma'am.
Okay. See, This is a tuning fork and it is vibrating. Can you see this vibrating? Okay. In this case, can you see this compression? See the layers are coming together. Hello.
Yes, ma'am.
Then it becomes, again it comes together, compression, again it comes together. So in between it is R. See, it is away. Can you see this? The layers are away from each other. So when there's a low pressure, so you can see this is a high pressure and these are the low pressure. Again high pressure, then low pressure. Do you understand?
Yes, ma'am.
Yes? Okay. All of you understood better? Hello? The same thing we'll see over here in a beautiful manner. So this is a sound waves, how it is traveling in air. So this is a tuning fork you can see. This is the tuning fork. This is the tuning fork on the left hand side. And when it is vibrating, you can see the compression and the rarefaction. So what I will first show you, the rarefaction. Can you see this rarefaction? See, there are no lines in between. Can you see this?
Yes, ma'am.
There are no lines in between. That means it is a low pressure. And if at all there are lines, they are away from each other. Can you see this? There are lines, but they're away from each other. So this is the region of rarefaction. Now let's come to the region of compression. See, the lines are very, just a moment, here. The lines are very close. Can you see this? The lines are very close. Can you see this?
Yes,
All
ma'am.
these lines are very close. Can you
Ma'am.
see this? Yes. So wherever the lines are very close, that is compression. And when the lines are very apart from each other, that is the region of low pressure, that is rarefaction. And now let's see what is wavelength. Okay, so let's talk about first, this is rarefaction and this is also rarefaction. So the distance between one rarefaction and the other rarefaction is the wavelength. You agree? Do you
Okay,
Yes,
ma'am.
agree?
ma'am.
Okay. And the distance between one compression, this is the compression, and the other compression is again a wavelength. Hope you have understood. It should be successive. Just now I taught you in this case. Let's go back here. There's a compression. Yes, beta, compression. So
Yes,
between
ma'am.
compression, it is wavelength. See, this is wavelength, this is wavelength. All are wavelength. Hope you have understood. It is equidistant. So you take any portion, any, it should be successive. Remember that. You cannot take one C over here and then you take one C over. No, it is wrong. You have to take consecutive. That means successive. If you are taking this, then you have to take this. If you're taking this, then you have to take this. Is it clear? It should be successive, consecutive layer. And then you get the wavelength. Either it is between two compression or it is between two rarefaction. Is it clear to all of you? Is it clear to all of you?
Yes, ma'am.
Ma'am.
Okay. Yes. Fine. Let's start with sound waves in ear. Now it's easy. I think it's almost repeated. So we will make it fast. Please continue.
The sound waves in air are longitudinal waves.
Continue.
Sound wave in air consists of compression and rarefactions. Air layer through randomly distributed
Though. Better it is though
yeah, air layers though randomly distributed are almost equal place for each other.
from each other. Then
When the right probe of the
wrong.
tuning fork moves outwards towards right, it pushes the air layers to the right creating more pressure. Therefore, compression regions of high pressure are formed.
Formed. Fine. This is what we have observed. Here you can see. See, this is the right. This is the right prong. These are prongs. Prongs. When it is vibrating on the right hand side, you can see the compression and the rarefaction on the right hand side, isn't it? Isn't it? Okay. Then on the right prong of the tuning fork, please continue.
When the right prong of turning fork moves inward towards left, it creates low pressure. Therefore, rarefaction region of low pressure are formed.
Then
This compression and rarefaction are passed on the next layer by the vibrating air layers. The process is repeated as long as turning fork vibrates.
tuning fork.
Tuning fork vibrates.
Okay. So this you agree or not? Because you have been reading the slides. Is there
Yes,
something
ma'am.
new to it? Boys, is there
No.
something new to it? We have already started, isn't it? In the last three, four slides is the same thing which has been highlighted, which has been sort of revised again, isn't it? Yes? Boys, did you understand?
Yes, ma'am.
Okay. Okay. Then what is written? The compressions and rarefactions are alternately formed. That is what we saw. That if it is C, then again you get C, but in between you get R. Again you get R. So it is alternate. You agree? CR,
Yes, ma'am.
CR. So it is alternately formed, isn't it? Okay. Next, only the
Only the compression and rarefaction pass on from one place to another, but the air layers molecules of air vibrate back and forth about their mean position.
so what is moving?
Position.
Compression and rarefaction. What is moving? Compression and rarefaction. That is low pressure and high pressure. Sorry, compression and rarefaction is high pressure and low pressure passing, but the molecules of air do not move. It only vibrates at its mean position, but they are not moving. Remember that. But they are vibrating at their mean position. But what is moving? The energy is moving. Is it clear? As in the form of compression and rarefaction. Is it clear to all of you?
Yes.
Yes, ma'am.
Last,
Only
last.
young. Yeah, when
When?
these sound waves fall on our ears, the eardrums vibrate accordingly and reproduce the sounds.
Now, my question to you. If the eardrum does not vibrate, what will happen?
Yeah, the sound will not its
Exactly.
sound will
So
not reproduce.
it will not go inside and we will not be able to register it, isn't it? The brain will not function. Hope you understood. That means for each and everything, it has to vibrate to create sound. You agree or not? You understood now?
Yes, ma'am.
Yes.
That means that means I go deaf. I become deaf if my eardrum does not vibrate. What do you say? What do you say? Say something better. If my eardrum does not vibrate, that means I become deaf.
No, ma'am. If
Yes.
someone
No.
Yes,
hears
yes, I
only one.
do. Yes, it is. You have to agree. If my eardrum does not vibrate, I will not be able to hear. So, for the sound to be heard, the object has to vibrate. Is it clear to all of you?
Yes.
Yes? Okay. Any problem regarding this slide? I have to keep on asking you, Beta, because you're not giving me any answer, sort of response that you really have any problem.
No.
So I have to, okay.
No, ma'am.
Now, sound waves are longitudinal waves. We'll do an activity. Okay, start. Start, Beta.
Stretch a silky and push
Slinky,
and
slinky, slinky. I will tell you what is slinky. Then, and push.
push and sound propagates in a medium as a series of compression and rarefactions.
This we know. We know sound propagates as compression and rarefaction. We know or not?
Yes. No.
Okay. Then,
In this wave, the particles move back and forth parallel to the direction of propagate on the
propagation.
distribution. disturbance.
Disturbance.
Such waves are called longitude waves.
Now you can see the particles are moving back and forth beta here. What is this lines? These are parallel lines. You agree? What are these lines beta? Is this parallel? Hello.
Yes.
Don't be silent, please. I'm asking you questions. I'm asking you something. You need to answer me. Please. Any of you take up the charge. Don't be silent, beta. It won't work. Okay? Fine. So, do you agree that the lines are parallel?
Yes.
Yes. So, what are
Yes, ma'am.
these? These are longitudinal. What are these?
Longitude.
Longitude.
Longitudinal waves. Hope you understood because it is parallel. Is it clear? I'm
Yes.
giving you hints and tips,
Yes,
beta.
ma'am.
Okay, fine. Now, here, let's do the last paragraph, beta.
There is another kind of wave called transmit waves. In this wave,
Transverse
the part
waves. Beta, read properly, please. Transverse waves.
I can't see it clearly, so I just read
Okay,
it.
then let's ask someone else to take it up, beta. Can we? Can
Okay,
someone
ma'am. No
else take up
problem.
the charge? Thank you, beta. Thank you. Can someone else start reading?
There is another kind of waves called
Transverse waves.
transverse waves. In these waves, the particles oscillate up and down perpendicular to the propagation of the direction of disturbance pull. It alternately
Alternately.
at one end. If you mark a dot, the slinky, the dot moves back and the forth parallel to the direction of the propagation of the disturbance.
Fine. So we are talking about, see, one wave we saw it is parallel. That means longitudinal waves, and that is sound waves. You agree or not? So sound waves are longitudinal waves. That is confirmed. There are another waves which is perpendicular. That means it makes 90-degree with the mean position. Is it clear? That is
Yes.
called as transverse waves. Right now, we are not going to be interested in transverse waves. We are interested only in longitudinal waves, that is sound waves. So, I just to let you know that there are two types of waves. One is longitudinal, and the other one is transverse waves. What is the difference? Longitudinal waves are parallel, whereas transverse waves are perpendicular. Is it clear? And what are sound
Yes.
waves, Vita? What are sound waves? They are longitudinal waves. Is it clear? Now let's see, this is a slinky. You can see this is slinky is like a spring. This slink is stressed. This is
When a
stressed. Can you see this? Yes. Slink is like a spring. What girls used to wear on their hands as their bracelet sometime.
yes, ma'am.
Yes, I hope you understood. So you get in the bazaar, in the market, all these things. Now what we do, we will coil the slinky first. Okay, and what we do, we hold the slinky from both the ends and we bring it close and we stretch it. So what is happening? A disturbance is created. And how does it travel? It travels like this. Now look at this. You can see the ones which are very close, it is high pressure, compression. Can you see this?
Yes.
Yes? And let's talk about the rest. These ones, you agree with me, beta?
Yes.
All of
Yes.
you? So we see this is what? This is longitudinal waves. So it is parallel, isn't it? It is going straight. The propagation is parallel in the form of compression and rarefaction, which are alternate to each other. Any problem? Tell me. Let's
Mm.
look over here. Now, this is not vibrating right now. See, this is a tuning fork first. What I did, I pulled it. The tuning fork is vibrating now. You can see over here. The
Yes.
one which is close to it, the particles, it became high pressure, that is compression. And one which is away is rarefaction. Is it? Now it is traveling. Now this compression is traveling. How does it travel? Look over here. See, this compression has reached here. You understood now?
Yes, ma'am.
Yes, ma'am.
All of you? So this is how it is
Yes.
traveling. Got it? The energy is traveling as in the form of high pressure and low pressure, that is compression or rarefaction. Any problem?
No.
No, ma'am.
Okay, beta. Again, in a series of compression rarefaction, purposely I've taken this. Let's see. See, this is the tuning fork. Can you see this over here?
Yes.
Someone's mic is on. Could you please put it off? Here, it is vibrating. You can see this is compression. Yes, beta. And see how it is traveling over here. Okay? Okay? Hope you understand.
Yes.
This one
Yes.
is reached here. The next compression has started over here. Now, this compression has reached here. This compression has reached here. Is it clear? See how it is traveling. Now, this compression is somewhere over here. This compression has reached here. New compression has come. You understood now?
Yes.
This compression has
Yes, ma'am.
somewhere here. This compression has reached here. So this is how it is traveling. Now I will show you everything together. Can you see this?
Yes.
First, it was only one. Can you see this? This was only one. And when it has reached, here it has reached. Hope you understand. This is the vibration of tuning fork that is making the wave energy propagate. That is making the propagation to happen. That is how the sound waves are traveling. Is it clear? From the source to our ears. This is how it is traveling. Any problem?
No.
So this is number one. This one comes over here. This is one. This is one. You got it? All these are one. This is two. This comes two, two, two. This is three, 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 and this is four. Is it clear?
Yes,
Yes,
ma'am.
ma'am.
All of you?
Yes, ma'am.
Yes.
Nicely.
Yes,
Any
ma'am.
problem? Any problem whatsoever? It
No,
could be
ma'am.
silliest of all.
No,
Don't
ma'am.
worry. You can ask me.
No, ma'am.
Okay, so things are very clear, right? That's the reason that I took this slide. Okay, now it's very easy for you to understand how it travels, how the energy travels in the form of compression and rarefaction. Thank you, Vita. The same thing. So it's just a revision, Vita. Just have a look. Now we'll take up compression. Can you see this range? The
Yes.
maximum is over here in the center.
Yes,
Can you
ma'am.
see this?
Yes,
Maximum
ma'am.
compression. So in between these two, it is wavelength. You agree?
Yes, ma'am.
This is lambda. You agree?
Yes,
Yes,
ma'am.
ma'am.
Hello. Okay, fine. Now you can see it is very away from each other. Can you see this layer? All these layers away from each other. Can you see this?
Yes.
Yes, okay. So in between two are see this one and this one. Again it is lambda. You agree? Do you agree or not?
Yes, ma'am.
Yes, ma'am.
Yes. Okay. In between two consecutive compression it is lambda. In between two consecutive rarefaction it is lambda. I hope I have taught you earlier, right? So you can see that the lines are so close to each other, isn't it? Can you see the lines are so close to each other in
Yes.
compression? And in case of rarefaction, the lines are apart. Can you see this? This is what you have to understand. Fine. Now we will put it in the form of wave here. Okay? So this is the distance between one compression to other compression is lambda. One rarefaction to other rarefaction is again lambda. Understood this much?
Yes.
Hello? This is a distance. Okay. Now we talk about amplitude. Can you see this? Just make it bigger. Here. Can you see this line better?
Yes, ma'am.
Yes, ma'am.
This is the amplitude. Can you see this line? See, I'm
Yes.
highlighting it better. It's just a revision part, but I'm just revising it. The things become quite clear now. I had drawn it. Remember in earlier slides, I had drawn. Remember that roughly I had drawn and tried to show you what is wavelength and what is amplitude. But right now you have got the ready-made ones. I think it's just a sort of revision. Things have become very clear to you. Am I right?
Yes, ma'am.
Yes.
So no problem whatsoever, beta.
No, ma'am.
Thank you, thank you. I mean, I feel good that you are understanding. So these are sound waves in here. Any problem?
No.
Finally?
No.
Okay. So this is an activity which will show that sound needs a medium to travel. Please begin. Please make it for, I want to still do one or two slides more.
Sound need a medium to travel. Sound is mechanical wave and need a medium
Salman, be
for
fast, please.
for
Propagation.
propagation. Sound travels through a solid, liquid, and gaseous. Sound does not travel in a vacuum.
Okay.
Activity: suspend an
An
electric
electric bell.
bell in an airtight bell jar. Connect the bell jar to vacuum pump. If the switch is pressed, we can hear the sound of the bell. If air is pumped out through the vacuum pump, we can hear the sound of the bell.
Cannot. Sorry, we
Can,
cannot.
we cannot hear the sound of the bell. This shows that sound needs a medium to travel and sound cannot not travel in a vacuum.
Okay. What does show that it is a mechanical wave? We have to produce, isn't it? If the thing does not move, so we have to vibrate, then only the sound will be created. What do you say?
Yes, ma'am.
Yes,
You
ma'am.
agree? Fine. And so it is mechanical because it has to be produced. It is like a machine. That's why it is mechanical. And if there is no medium, it will not travel. So it needs a medium for its travel. Sound travels through all the matter that is solid, liquid, and gases, but it never travels in space where there is no air. That means it is vacuum. This much have you understood?
Yes, ma'am.
How to show? What we'll do? We will put a electric bell. This is a bell jar. What is this, beta? This is the bell jar. Is it clear?
Yes,
And
ma'am.
this is the electric bell, and this is the bell jar. Is it clear?
Yes.
Okay. Okay. And I will fix it with a vacuum pump. Can you see this? Here is the vacuum pump. You got my point?
Yes, ma'am.
Okay. We will connect this bell jar to vacuum pump and you switch the press. When you switch the press, when you switch it on, the electric bell starts ringing. You can hear the sound. Yes or no?
Yes.
Because there is air inside. What is there, beta? Air
And
inside. Slowly from the vacuum pump, I start removing the air. What will happen? The the intensity of the bell will decrease. Am I right?
yes, ma'am.
And when the whole air will be sucked out by the vacuum pump, I will not be able to hear any sound. Am I right?
Yes, ma'am.
So sound will become faint as we are sucking out the air from the bell jar. All of you agree, beta?
Yes, ma'am.
So it confirms that sound travels through the medium or in the presence of a medium. And when the medium is removed, there is sound, no doubt about it, but we cannot hear. See, the bell is ringing, but we cannot hear the sound. Is it clear?
Yes.
All of you,
Yes, ma'am.
children, ninth standard, please be interactive. I need at least 4 or 5 yeses, please. Huh? I appeal to all of you.
Yes, ma'am.
Take
Yes,
part. You will
ma'am.
enjoy. I'm telling you. Okay. So this much have you understood completely? This activity, all of you have understood?
Yes,
Yes,
ma'am.
ma'am.
Okay. It's the same thing. It's the same thing. See? Bell. So it's a doorbell. You can see it's a doorbell which is fixed inside the bell jar, but it's inverted, and there's a vacuum pump over here, and air is being evacuated. And when it is completely evacuated, you cannot hear any sound. See, you can see over here, you cannot hear any sound.
Yes.
Okay, it does not reach the ear. The same thing in a different format I've shown you. Because I've shown the circuit. Can you see over here? This is the
Yes.
circuit diagram. Okay, that's what I've tried to show you. Now, what are the characteristics of a sound wave? Is someone who can speed up We are just trying to revise it. Please, one of you.
Ma'am,
Can
can
I
I read?
Yeah, yeah, sure.
Characteristics of a sound wave. Sound wave can be described by its frequency, amplitude, and speed. Sound
You
can
agree?
be graphically
You agree? Frequency, amplitude, and speed. Can we agree?
Yes, ma'am.
Yes,
Okay.
ma'am.
Second,
represented as a wave. There is a change in the density and pressure, and sound moves in a medium.
what is density and pressure? Compression and rarefaction. You agree?
Yes, ma'am.
Yes,
Yes.
ma'am.
Third,
Compression and the regions of high pressure and des- density
density
where the particles are crowded and are repre-
represented
represented by the upper portion of the cloud called
crest.
crest.
So this is what new thing that you have understood, right? Crest. You have understood a new thing which is called as crest. Okay? Okay. So what is crest? I will show
Raref-
you. Then rarefactions.
Continue, ma'am.
Yes, yes.
Rarefaction are the regions of low pressure and density where the particles are spread out and are represented by the
Represent.
lower portion of the cloud called can't
Trough.
see that word
Trough. Troughs. Trough. Read with me.
trough.
Trough. Yes. Okay.
Trough.
Fine. Then
The distance between two consecutive means these words are getting blurred.
compressions. Okay. Okay. I will read it. The distance between two consecutive compressions, that is crest, or two consecutive troughs, are called wavelength. Now, did you understand wavelength?
Yes,
Yes,
ma'am.
ma'am.
So, what is the crest? The topmost compression. What is trough? The downmost compression. Do you understand? And what is the
Yes,
denotation?
ma'am.
What is how it is denoted? Lambda. What is denoted? Lambda. And what is the unit? Meter. Is it understandable? I will
Yes,
just
Yes,
ma'am.
see, show you over here. Here. What are these? These are compression. This is compression, beta.
Yes, ma'am.
Hello.
Yes.
Agree,
yes,
all of you? Okay.
Yes, ma'am.
This is rarefaction.
Yes, ma'am.
This is rarefaction.
Yes,
Agree?
ma'am.
Okay. Now let's see the wavelength form. Here. This top one is called as crest. What it is called as, beta? Hello. Crest. And these
Crest.
bottom ones are known as trough. Upper one is known as crest. Bottom one is known as trough. Is it clear?
Yes, ma'am.
And these are the amplitude. This is also clear.
Yes, ma'am.
In between two compression, it is wavelength. That is also clear.
Yes, ma'am.
That's it. And wavelength is distance. What is wavelength, beta?
Distance.
Distance. Hope you understood. So distance goes straight and pressure goes 90 degree. Is it clear?
Yes, ma'am.
Is it clear? Any problem?
no,
No,
ma'am.
ma'am.
Boys, okay. Things are clear or no? Tell me first.
Yes, ma'am, all clear.
Yes, ma'am. Clear.
About this, how the sound waves travel, what sound wave is made up of. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay, fine. Thanks a lot. And on Monday we meet. But before that, I will be giving you certain